Okay, Jordan, let's start.
Oh, sure. Hi, everyone. Welcome to the online seminar on the math foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2Sigma. It's my real honor to introduce our prestigious speaker, Professor Xi Chen. Professor Chen is an associate professor at Stern School of Business at NYU. He is also an affiliated professor to computer science and Center for Data Science. He has made many great contributions to high-dimensional statistical learning, online learning, large-scale stochastic optimization, and applications to revenue management and crowdsourcing. He received NSF Career Award, Outstanding Faculty Research Awards from Google, Facebook, Adobe, Alibaba, and Bloomberg, JP Morgan, and was featured in Forbes' list of 30 under 30 in science. The title of the talk given by Professor Chen today is Robust Online Learning and its Applications to Assortment Optimization. Please join me in welcoming him.
Okay, thank you everyone for attending my talk. It is a great pleasure to give this talk. So as this already been Friday afternoon, so I won't give a too technical talk. So I will give a brief overview of some of my research related to online learning. And then I will zoom into one particular project on the robust online learning and its application like to recommender system. So, okay. So I would say like a classical machine learning is facilitated to understanding the given static data. There's a lot of like emphasis on online learning these days, especially for bandit or reinforcement learning. And many organizers are like kind of contribute a lot to this field. So this is importantly true like for me because I'm a professor from the business school. So if you look at all this kind of business applications, it's not only about learning. It's more about like a decision making. Okay, so just give you some examples. For example, you trying to understand the customer demand with respect to the price. We understand that if you give a higher price, the customer demand becomes lower. If you give a lower price, your customer demand becomes higher. But so the question is that it's not only trying to predict if I give this price, what will be the chance customer will buy it. This is only like one thing. But in reality, it's more difficult, like you just need to give a right decision on the price because this involves a lot of other factors and the constraint, like inventory constraint, and also the customer like psychological reaction to this price. And similarly, like for recommendations, the most important thing, like you give like sequential recommendations to the customer. And this is especially true like for trading, like if you can make you can try to infer the signal of the stock price going up or going down tomorrow, but it's still very challenging how to like adjust your portfolio. So the online learning and decision making indeed involves a sequence of interactions between the platform and the many agents. So a general paradigm I'm thinking about can be characterized by this picture, where you have an online platform, okay, and this online platform we're just using like e-commerce, like for example Amazon as an example throughout the talk, but you can consider as many different kind of online platforms. And a customer arrives, okay? And a customer, like for example, you can recommend a few products and a customer can click the one that he or she is interested in, okay? So usually we're like trying to model the customer behavior using certain probabilistic model. So I'll give like one particular probabilistic model in today's talk, but you can imagine there's hundreds of thousands of ways to trying to characterize the customer behavior. Okay? So for the job of the online platform, he needs to give a decision when the customer arrives. And this decision usually includes like a price or recommendation, as I just mentioned. And what we will observe? He will observe two things. One is that he can characterize the customer behavior. For example, he can, he can see which product the customer clicks on, and he can even go into like a more refined behavior. For example, how long the customer spend on like a particular product, like even, like with what is a browsing behavior. And if he just compare with some other product, and also in addition, the customer really make the purchase, he can get the revenue. He can get the online platform can get the revenue, and all this revenue and the customer behavior information you can think it should enter into the online platform into like their learning system. And learning system will gather this information and trying to make new decisions on the price and recommendations. And hopefully these decisions are better than the previous decisions. So here are a few challenges. So first, the challenge is that the underlying probabilistic model, like which you're trying to use in this model to characterize customer behavior, is usually unknown and needs to be learned on the fly. So this is where like our machine learning comes. And in particular, today's talk will think about, like no matter how fancy or how good your probabilistic model is, inevitably there will be some customers do not follow the model. And how do we like address that challenge so that the robustness comes into the play? Okay, so this is the one thing. And second thing, in addition to learning in this kind of online platform, the real-time decision need to be made like on the time. So I'll give you some examples, okay? So first example will be like, for example, the online recommendation. So as you can see, for example, this is the Amazon platform. When you search for like, for example, headphones, and Amazon platform will have like a few spots. For example, there's a 6 spots, and Amazon platform will recommend you like this, the 6 like headphones on the top of the page. And usually today's talk, we will restrict to one type of recommendation, which we call the substitutable products recommendation, which means that we usually assume like you're given the 6 products, the customer will only buy 1 product from this, or he can leave the system without any purchase, but we don't generally consider a case you will buy like 2 headphones in the same session of purchase. Okay, so and we're like trying to use trying to combine machine learning and trying to characterize the customer behavior using a probabilistic model from economics, and this is called choice modeling, and we'll talk about it a little bit later. And this is also another very fancy, like kind of assortment optimization application is connected to like a very interesting startup. It's called a Stitch Fix. Now it's not only a startup, it's already been on the market. But actually this company is very interesting. So like if you subscribe their membership, and forever like a week or 2 weeks, they will mail you a box. For example, when the winter comes, they will mail you a box, maybe with like 5 different kinds of like sweaters, and with some jewelry, some other small things in the box. And usually you will pick the ones that you really like and return the rest of them. So the question is that for every month, how does Stitch Fix company decide in a particular box what kind of like 5 different clothes to mail it to you? Okay, so I have been doing a lot of research on this domain. I just list a few papers. So for those who are interested, you are welcome to look at these papers. And today we'll particularly talk like one project on this, like related to this recommendation. Okay, and in addition to recommendation, another like thing that you can think about, like what we call it like dynamic pricing. Okay, so it's still like related to e-commerce, and this is a joint project with this is a joint project with like Alibaba. So as you can see, this is like a, this is like a, for example, this is called the Tmall supermarket. It's just like you can think about like Walmart supermarket or like Amazon Fresh. So where you have like kind of all the products, but this kind of, for this all the products, you need to determine the price, and this price is not static. It will be changing over time. Okay, the changing depends on the popularity of the product, the customer reaction to the price, and maybe in the holiday seasons you need to give like certain kind of a discount. Okay. So like in the dynamic pricing, of course, we need to understand the customer behavior with respect to a given price. For example, just the simplest case is that given a certain price, what will be the chance the customer will purchase this product? But they still have some particular challenge. When I work with Alibaba, like one challenge they give to me that for some products, for example, for this one, this only have like a weekly sale is only like 4. Okay, so for some product you have weekly sale maybe like 100, that's easy. But for all this kind of product, you can see the weekly sale is relatively small. So the weekly sale is relatively small. It's then we learn the machine learning. We understand that it's very difficult to predict the customer reaction with respect to the price, okay? Because you have a limited amount of like training data. So to address that one, actually we're trying to combine like the clustering technique with the dynamic pricing. And if you're interested, you can look at this paper. So I will not go into details of that, but this can also give you another application of this kind of online platform interaction with the customer. So there are a few components that you need to learn from the customer reaction to the price, and the online platform will observe the customer purchase behavior and using that one to adjust the price for the next period. And so by the way, like to deal with this low sale product, so actually we adopt a very intuitive idea is that we're doing the clustering during the, in the online fashion, and while we are giving like the pricing. So which means that, like we will group the product with similar demand function, not similar features, but we like the similar demand function, which means the customer reaction behavior. So we'll cluster like the product will receive the similar response from the customer into like a group. So that once we'll like group them into like kind of a group, we get more training samples. So then we can get like a better prediction. Then this can be combined with like the online learning to give like a better pricing. And this algorithm has already been run and deployed by like Alibaba. And finally, another like very brief like application I'll mention today is like cross-sourcing. I have been working on this cross-sourcing for like about 5-6 years. So actually the cross-sourcing is a problem-solving process where a large number of tasks are outsourced to a distributed group of workers with varying expertise. Like one of the most popular platform for cross-sourcing is Amazon Mechanic Turk. You can see like even in 2012, there will be like more than 500,000, so 500,000 of the workers from like 190 countries. They are working on this Amazon Mechanic Turk. And I will give you some examples. And one of the most intuitive like application of like using this cross-sourcing is for image classification. So actually everybody knows that the deep learning really booms out becomes due to like the ImageNet data set, which motivates all kinds of like deep learning architectures. And the ImageNet is like contains like a few million images, and these images actually obtained their training label by just using like this kind of Amazon Mechanic platform. And you can also using this for like URL ranking, opinion gathering, even more complicated tasks like proofreading. So for example, as I mentioned, like the ImageNet, Professor Fei-Fei Li from Stanford at that time, she and her team like collected 14 million images crossing like more than 20,000 categories. And so then this becomes a critical step in the success of deep learning. But question that given all these images, how do you obtain like these categories, especially this more than 20,000 categories? And the solution is just about like cross-sourcing. So I'll just give you a very simple example, and this is called the Galaxy Zoo. So where like the, like this, the pictures is by like telescope. So they take the pictures like tens of pictures in every second. And then they'll ask the people to classify like the capture the galaxy. So there are many different shapes. I just consider like the simplest case where you can only consider two main shapes. One is called the elliptical galaxy looking like this, and the other is spiral galaxy. And so the cross-sourcing that you distribute the tasks to the workers, and the workers, you gather the feedback from the workers. For example, in this case, two workers will claim this will be like 1, and the other worker claim this will be 0. So like you aggregate these answers, for example, by majority vote, because you understand like a worker will not perform, like in the consistent way. Some workers have more expertise. Some workers are more like kind of random, and even some just like a robot just trying to make as much money as possible. And you can do it for all like kind of images. Of course, there's no free lunch. For example, you can assume like each label, no matter it's correct or not, because even with kind of this aggregation, you will not know like whether like they will, like the labels provided by the workers are correct or not. So you will see like each label only has a certain cost amount of money, for example, like 10 cents. So like the goals of the cross-sourcing is kind of infer the true label of each item, infer the expertise of each worker, and we want to have an effective budget control procedure. So the challenges in practice is that, you need to make the decision. So the decision contains how to adaptively select the next worker, what will be the right time to stop the data collection process. You understand there's a trade-off. If you have a very long time, then you will need to spend a lot of money. But if you just cut off, for example, every image only receive like 3 labels, then the quality becomes the issue. Okay, so the final estimate is that how to combine the answers from different workers to infer the true label of each item. So then you can think like Amazon Mechanic Turk is a platform, and there's a worker comes in one by one. You use some probabilistic models to model like the worker's behavior, and the platform need to make the action whether you want to assign tasks to this worker, how long you want to wait, and when to stop this data collection process. And it receives the raw label from the workers. Okay. So here are some like papers on this regime, and so I will not go into details of that. So this is just like a very brief introduction of like this kind of online learning platform that I've been working on. So as I mentioned, so if you really deploy this platform like into reality, like for example, if you're working with a company, so actually the the biggest challenge is not whether you are using like for example UCB or Thompson sampling, or like how fancy your algorithm is. The most challenging part comes from the fact that you are using some probabilistic model to understand the customer behavior, but in many cases the customer are irrational, and there's no perfect model can capture all the different behaviors of the customer. So for example, as I mentioned, like in the pricing, you assume this is the demand. You can view this demand as the purchasing probability, and this is the price. And we understand, the demand, if your price goes up, it goes smaller, and the customer purchase probability will become higher. But it's not necessary you should use like a lower price, because if your price is lower, although more customer will purchase it, but your revenue becomes smaller, because on each product, even you sell it, your revenue from the profit from the product becomes very limited. So actually, the best price is that you are searching for the price which maximizes the price times the demand function. So usually we'll assume this kind of thing, with the price decays, there's a very nice shape. Usually you can assume this is kind of a convexity or like the monotonically decreasing function with respect to the demand. But in reality, you will find this may never be the case. There'll always be the irrational customer. For example, I just love the Apple product so much. Whenever it launches a new iPhone, no matter how expensive it is, I will just go into purchase it. And sometimes the customer think that even if you have a product, especially for the luxury product, even it's very expensive, people are willing to pay the money. But if you make the discount, people are not willing to pay that because people think maybe this model is not good, or I just buy this handbag, it's not fancy. So all this kind of behavior happens so that if you want to use this a single function to characterize the customer behavior, this may not be working in practice. And also like for the assortment optimization, we'll talk about this. The customer, when you give them a lot of choices, and we usually have some model to characterize how customer make the choice. But this kind of model can be frequently be wrong in practice. So this part has has not been paid too much attention in the especially in the business domain. But as a statistician or machine learning scientist, we really think about this, because actually as George Box said many years ago, as he said, all models are wrong, but some are useful. So the question is that what if a customer does not behave according to assumed models? Okay. So then the question that how, in the statistical jargon, the question that how do you deal with model misspecification in the online setting, in the online decision-making setting? So actually we work on this for several projects. And the one project is, as I will spend a lot of time today, is on this kind of recommendation system. This is a joint work with Akshi from Microsoft Research and Yining Wang from University of Florida. And also we'll have a following up paper on doing the robust dynamic pricing with demand learning. And this is a work on also with Yining Wang. So today's talk will mainly focus on assortment optimization for the recommendation. Okay, so let's give a very 2 slides of brief introduction to robust statistics. I think many of you are expert in robust statistics. I really do not need to spend time on it, but I just give a very intuitive introduction. So the model we'll think about today is very classical one from Huber's epsilon contamination model. It's this proposed by P.J. Huber in 1964. So the idea is very simple. You have NID observations from a mixture distribution like x1 to xn. So with 1 minus epsilon probability, it's drawing from a standard or the true a common distribution p theta. So the p theta is your true model with unknown parameter theta. So for example, you can just think that's a normal with mean parameter theta and standard deviation 1. And on the other hand, with epsilon q. So q is the outlier distribution. Okay, and we put no assumption on the outlier distribution. It can be any arbitrary distribution. And epsilon is a parameter between 0 and 1. So it's kind of a corruption proportion, right? So you can see epsilon proportion of the data were corrupted by this outlier distribution, but we do not know which observations are outliers. Okay, the key part is that if you know this, then you just get rid of this outlier. But the question is that you do not know which observations are outlier. So the question is that given the observations x1 to xn, how do we estimate the underlying parameter theta? So we know that without any corruption, corruption, so if your epsilon is 0, you just get rid of this. So if you are only trying to estimate a normal distribution with mean theta, standard deviation 1, and you can understand like the sample mean will be like enjoys a lot of good properties. But this is from like statistical 101. But we understand in this kind of epsilon contamination model, even a little bit corruption, like a little bit noise here, can drive your mean to be very large. Okay, so that's you can arbitrarily corrupt your sample. The question is that how to handle like the corruption. Okay? So then we need like some robust statistics. Okay, and the most straightforward robust statistics in this case is kind of a median. Okay, so that's just instead of taking the sample mean, you take the sample median of x1 to xn, and you can prove like certain type of high probability bound where the median subtract the true parameter with high probability. It will be bounded by like some constant times like epsilon plus 1 over square root of n. And this bound will also show in like in today's talk when we consider much complicated problem. But the idea is that this epsilon is the corruption proportion and the 1 over square root of n is the standard parametric rate. And so this just contains like these two parts. Okay. So when the theta is, of course, this is like very straightforward for like the only one-dimensional case. So if it's for higher dimensional case, originally Tukey has some very important notion called Tukey steps. It's basically the idea is they generalize the median to a higher dimensional, space. But Tukey steps is extremely difficult to compute. It's even difficult to approximate. And so there's many groups from like Anker Moitra, from many other people, like propose efficient learning algorithm for this problem when the D is much bigger than 1. Okay, but I will not go into details of that. So this is my like very gentle introduction to the robust statistics. But today's talk we are considering like the business problem. Like for example, you're making sequential recommendation. So a very natural thing that we'll study is that we'll extend the Huber's epsilon contamination model into the online setting. So we'll consider like this. So you have a finite horizon, t from 1 to capital T. Okay, and each observation is either a typical observation from p theta with unknown parameter theta you are going to learn, or it can be from outlier distribution QT. And we'll assume that's because it's an online setting, so we assume that the QT can be arbitrary and it can also change over time T. And we consider a very strong like adaptive adversary, where means the outlier period. So when the outlier will, you can see when the outlier customer will come in, and what will be the outlier distribution QT can be adversarially and adaptively chosen depending on all the previous information. Okay. So we only make one very minimal modeling assumption. So remember in the Huber's epsilon contamination model, so the observations are chosen IID, but of course you cannot assume that in the online setting. So we only make such assumption called the bounded adversary, where the number of outlier observations is at most epsilon T. Okay, is at most epsilon T. So in today's talk, we'll zoom in and talk about this robust dynamic assortment optimization. But I believe this kind of framework is a very general framework that lies between the stochastic model and the 4D adversary model. So it's not as conservative as 4D adversary model, but it can efficiently handle a lot of outlier behavior, especially like for example during holiday seasons and things like that. Okay, so we'll give like so we'll talk about like the model we'll adopt today, but we're giving a little bit background of like a dynamic assortment optimization. So as I mentioned, dynamic assortment optimization is a particular kind of a recommendation system. And the question is that how do you select a subset of substitutable items to maximize the expected revenue? Okay. So key in this is to understand the customer purchase behavior. So and in borrow from like economics, one of the most popular behavior like a model is what we call it the choice model, discrete choice model. The idea is very simple. You are given like a set S is offered. And the question is that which item the customer I will make the purchase. Okay, so this is the PIS what denotes the probability the customer will select item I when the set S is offered. Okay. So there are some popular choice models. One is the multinomial logic model we'll talk about, and the more complicated one is nested logic model. And actually, just to show you how important this model is, actually 2000 like Professor David Madfagen from economics at UC Berkeley, he won the Nobel Prize for the development of theory and method for analyzing discrete choice model. So this is like a multinomial logic model. It's extremely straightforward. So let's assume you have n products in the pool. you just associate each product with a non-negative utility. Okay, actually this is not utility, it's exponential of the utility more rigorously, so that it's non-negative. And sometimes we just call it preference score. Okay, we want to VN at the preference score, like how like just a customer preference for each product, 1 to n. Okay. And PIS denotes the probability the customer will select item I if they are offered the set S. Okay. And this is denoted by VI, which is the preference score of the product I plus 1 plus over 1 plus summation of VJ. So this 1 denotes the no purchase. Okay, this 1 stands for no purchase, and VJ is all the preference score, like the summation of all the preference score in the assortment set S. Okay. So the classical literature from economics and from operations on this assortment optimization, that how do you make the recommendation? They assume, in the simplest case, they assume all the VIs are given. Okay, so you are given like all the VI. So then this question becomes a combinatorial optimization problem. So you can formulate the problem in this way. So this RI is the revenue for the item I. Okay, so this RI is revenue for the item I, and the PIS is the purchase probability. And this summation is just the expected revenue when offering the set S. So they will denote by RS. And we're trying to find the set S which maximizes expected revenue, but usually the S has this cardinality constraint K. Okay? Because, for example, in the Amazon, it cannot display like 1,000 products on the website, and especially there's a lot of psychological study showing that people usually make the best choice among, like, for example, 10 products, and if you are going beyond like 25, like the people choice becomes very, very poor. So this case is just like a constant to bound the set, the cardinality of the offered assortment. And this is a combinatorial optimization problem, but actually this has a very, efficient algorithm. We'll briefly mention that by some searching, some binary search. So this is the most simple, like a multinomial logic model, and you can extend it. Okay, so for example, you can, so in many cases, the people make the selection in the hierarchical way, in the tree structure. So this gives the very natural, we call it nested logic model, where, for example, the people first select the category codes, and among the selected category, the people select a particular product. We're not going to detail that, but for those interested, you can take a look at that. And of course, you'll see, like, usually nowadays, the product has the feature information, so you can easily extend it to like the contextual logic model. So where, for example, the VTI, so you can also consider like the kind of time evolving case, where VTI is the utility parameter of the product I at time t. Okay, and XTI is that at each time t, the customer will observe like a d-dimensional feature vector of the item I. So this feature vector can change over time, and the beta star is the underlying parameter to be learned. So here I just consider a linear model, but if you want, you can either fit like a deep neural network on that. So this just to give you an example. For example, for this particular sweater, and this has like feature information. So some feature informations are static. For example, if it's a sweater, its color, its style are static. But some feature informations, can be changing over time. So for example, whether it's a holiday or not, and the rating of the product, this can just change over time. And certainly, like with this kind of model, you can just trying to capture the evolving behavior of the utility. Okay? So as I mentioned, when the parameters, so let's go back to our the problem, the assortment optimization problem. As I mentioned, no matter how complicated this choice modeling is, as long as you know this probability, this becomes a combinatorial of the optimization, and it will always be able to solve it. But in reality, the utility parameter, the customer preference scores, are almost never unknown and need to be learned. And this is especially true for the fashion industry. So for example, when you buy like kind of a luxury watches or this kind of thing, so the historical data are not enough or available for estimating the choice probability. And there are many earlier works has been studied for this kind of a dynamic assortment optimization framework. So actually, I will give you just to extend this kind of a thing in the online setting. I will just give you a one slide summary. So the idea is very simple. So this is seller, this is the buyer. So there's consider that's a horizontal T time period without any inventory constraint. At time 1, the seller offer a assortment set S1, and the buyer will make the purchase, and the buyer purchase information, or the buyer can leave the system with 0 without any purchase, and this information will come to the seller, and seller will revise their recommended set, and it will come to like I2, and so on and so forth. Okay. So with the time T periods. So the key challenge in this setting is that, as I mentioned, the utility parameters are unknown. So the platform needs to learn some dynamic policy that simultaneously learn the underlying utility parameters and make the decisions on the assortment ST. Okay. So of course, as we learn like online learning, we know like the goal of the seller is to maximize the total expected revenue. So which is summation of the expected RST. And but the question that, like if you only put this as a goal, then the question that if I give an algorithm is generate like unexpected revenue $200, you give an algorithm on $300, we don't know like what will be the ceiling, the best. So instead we'll consider using like, instead of like maximize the revenue, we'll adopt the equivalent criteria which saying that minimize the regret. So which we are just bound the gap from the expected revenue of your strategy, your algorithm which generates assortment ST with respect to the best expected revenue of RS star. So RS star is, as you remember, this is the best assortment. You're just solving a combinatorial optimization problem, and you're assuming all the utility parameters are given. Okay, so this is just like the setup for the like the setup for the like online assortment optimization. But as I mentioned, the key issue is the model robustness. So in reality, you can assuming like a multinomial logic model, but although it's widely being proven to be like useful in practice by a whole bunch of economics, but the problem is that it's still the customer may not just follow the ML model. So that it's clearly we should extend this using what we just introduced by epsilon contaminated model, where we just modeling each customer either will be a typical customer or outlier customer. So in this talk, we're just assuming the typical customer will make a purchase according to the multinomial logic model, and you can further extend to nested or like contextual case, and outlier customer will just make a purchase arbitrarily. And like we're assuming the arrival time and the choice of outlier customer can be adversary adaptive. And why we need to arrival time can be adversary, because this can be useful for modeling, especially for the holiday season. You expect like a whole bunch of outlier customer will just come in a very small amount of time, and it's very clustered and during consecutive time periods. And the modeling assumption we made is only like bounded adversary. As I mentioned, the number of outlier customer is at most epsilon t, because if it's beyond that, it's too many outlier, you cannot learn any useful information. Okay. So a little bit related work. So actually, so there's 2 lines of research. One is on the dynamic assortment optimization. The earlier work, and from 2018, I studied this problem with my collaborators on the uncompetitive ML model, which means do the online learning for the multinomial logic model without the cardinality constraint. Your assortment set can be as large as possible. And also there's a lot of research during the similar time on the competitive ML model. Especially this group from Stanford, they proposed like a very novel UCB algorithm, Thompson sampling, and I give like a lower bound for this algorithm, and then we will extend to the nested logic model. And there's a lot of research on contextual time involving multinomial logic model. I will not go into details on that. On the other hand, there's another line of research very hot in machine learning. It's called like doing robust machine learning or robust statistics. So there's a lot of effort trying to tackle the epsilon contamination model, proposed like computationally efficient algorithm. And recently there are some papers on doing like a robust multi-arm bandit, which shares very similar spirit as like our algorithm on like the robust assortment. But the key challenge in directly adapting their algorithm is that if in the assortment you choose each like set as a possible action, you have like n choose k possible actions. So this is kind of too large. So that if this going to the regret bound, it just becomes too large. So we need like twist the algorithm to get like a new algorithm to get like the optimal regret bound. Okay, so this is just like the summary of the regret bound, and then I will dive into the algorithm. So it's very helpful to compare with the case where there's just no outlier. Okay, so so here there is the outlier with epsilon t outlier, and this is the regret bound with no outlier. So actually, without the outlier, so the correct bound is square root of n times t. So n is the number of products, and the t is the total time periods, and it's also the matching lower bound. And for the with the outlier case, the lower bound we show is epsilon t times square root of nt. So this is like epsilon t is the price you need to pay for being robust, because this epsilon t proportion of the customer, they're just arbitrary, so that you just cannot expect anything from them. And but on the other hand, the upper bound is in this case, so it's almost a matched lower bound except for this factor k. It's epsilon t k squared plus square root of ntk. But usually, from practical point of view, we don't worry too much, because this cardinality constraint, as I mentioned, if you're in the Amazon homepage, you just cannot offer too many like products at the same time. Otherwise, it's both clustered for the website and also make the customer extremely difficult to make the choice. So usually, if your k makes as a constant, then it's almost a matching upper and lower bound. But of course, in the technical wise, it's a very interesting question. Can we get rid of this k, just as in the no outlier case? And we don't know how to do that at this moment. Okay. So now we'll give details of the algorithm. So the algorithm is very simple. We base our algorithm on a very popular framework in the banded literature. It's called active elimination policy. Okay. So the idea is as follows: you divide the entire time horizon into epochs. The tau is from 1 to 3, and each epoch has 2 to the tau time periods. And in the banded literature, is usually like doubling trick. And then we maintain an active set, A tau, consisting of good items. Okay, so these are the items that you should recommend. In other words, these items should contain the S star, which is the optimal assortment if you know the utility parameter. And this S star should be a subset of A tau. So this is a key property we're going to maintain. Okay, several key ideas. The first, that after each epoch tau, we'll try our best to remove the bad items, which means the items that are unlikely to be within the optimal assortment. And within each epoch, we're using some randomized exploration strategy for the still like active items in A tau and trying to learn the utility parameters. And the key thing that we're going to guarantee that for all the epochs, the optimal assortment S star will be contained in the A tau with high probability. So the question that, so this hopefully is a very clear framework. So the question that, how do we remove the bad item, and how do we, how do we do the random exploration? I should answer the questions on the line, or we should put in the end. Slide is changing. I just trying to answer the question. So one attendee. Should I answer the question in the middle, or?
I think we can save the question to the end.
Okay.
Yeah.
Good. So okay. I want to clarify, like this S star, we are using as a benchmark is only for the typical customer. Okay. So we're not trying to match any behavior of the outlier customer, because it can be arbitrary. So to be clear, this S star is the optimal assortment for the typical customer, but following like a multinomial logic model. Okay. So step one. Okay. So remember these two steps. The first step is that how do we remove the bad item? So we think about this problem. So what you determine if the item is good? Okay. So the item is good in the sense that if the item I, if you contain that, you're just trying to solve optimal like assortment optimization problem. If this item is good, it means that no matter you decide to include this item or not to include this item, so which means that if you like exist assortment S that contains the item I that almost approach the best revenue that you can expect, then this item is good. So in other words, we can consider in the opposite way. Okay. So what will be considered an item is bad? Okay. So item is bad that you can see like these two things. So this is trying to estimate the expected revenue, but of course we know we don't know the underlying utility parameter. So we're just using the current estimate of the underlying utility parameter plug in to compute this expected revenue. So the left-hand side and the right-hand side are almost the same. The only difference that for left-hand side, we have a hard constraint. We need to include the item I. So guess what? So this is saying that the optimal expected revenue when you force the assortment to contain a particular item I. And this is just you do whatever, like kind of you're just trying to find the optimal expected revenue for all the possible assortment. So if you decide to, once you include the item I, if it leads to a big decrease of the revenue, and this decrease will be characterized by this delta epsilon tau. So this, if you like, once you include this item, and this leads to your big decrease of the revenue. So this means this item is bad. So this is a very intuitive idea, right? And so this is what we call the confidence level. It's pretty much like the confidence bound in the UCB. It depends on the epsilon and depends on the tau. So tau is the epoch, okay? So with your epoch is decreasing, like your margin becomes smaller and smaller. This is like very intuitive because as your epoch, like epoch increasing, like your estimation becomes more and more accurate. So like you need to like shorter interval to exclude those like bad items. On the other hand, if you are like the corruption proportion epsilon becomes larger, then you need a larger confidence interval because you have like more possible of outlier. Of course, there's an issue that to construct this confidence bound, you need to know this epsilon. There is an adaptive algorithm that can be used without any information of this epsilon, and it's called the multi-layer elimination risk strategy, and from this Rint paper. So I will not go into details of that, but just to give you a reference, and you can also look at our paper. There are details of how to make the algorithm adaptive to this epsilon. And this optimization can also be solved by some binary search algorithm. I will just briefly mention that it's just very easy to implement for this kind of assortment optimization problem. Okay, so this is like how do we determine like what will be the criterion for a bad item. And the next thing that how do you like trying to learn the utility parameter? Now that is fairly easy. So the idea is as follows: you randomly select the item I from like the assortment, and you're trying to find the best assortment such that I is contained you force this I to be in this assortment. So then you just record two things. One is Ni with the number of times I was purchased when like S is offered, and the other N0I is like what will be the like probability you can see like the when I is offered in this S, but I is never purchased. And you can try to formulate the expectation of the times Ni and N0I without any outlier. It's just a proportion to this two quantity, and you can just take the ratio. Okay, but of course, with outlier you need to bound this more carefully. But anyway, you can just using this procedure to get an estimate of the utility parameter, and then you can repeat the procedure to removing the bad items. So let's just do a little bit summary. So the step one is that you for each time period t in the tau epoch, you randomly select the item I. You make sure like your item I is contained in the assortment. You offer this assortment to the customer, and you record the customer purchase behavior. So I will be the time I is selected here and purchased, and 0I is like I is selected but no purchase. At the end of the epoch tau, you just update your utility parameter estimate by taking the ratio, and for each product I, you just trying to verify this inequality. If you include the item I and your expected revenue based on the current estimate have a big decrease, big drop, and you just get rid of this item. Okay. And finally, I just briefly mention that you should this optimization is fairly simple. This you just can do it by a binary search procedure. So the idea is very easy. You just trying to always find a valid lower bound for this revenue. So you can just do a little bit of manipulation. So for example, this R low is you are trying to test whether this will be a lower bound. And so you're just trying to make sure, because Ri is always in the assortment. So you just make sure like, Ri minus R low and Vi hat plus all the possible item J in this assortment. And this boundary is less than K minus 1. And you want to see this one. And if this holds, which means R low is a valid lower bound. You just do a manipulation of this inequality. And now it's very simple because whether you want to check whether it's a lower bound, you just want to make sure, you just want to make this part, because this R has been fixed, and you just want to make this part to be as larger as possible. So you just rank all the items with respect to Rj minus R low times the Vj hat. You just rank them, and you choose the largest K minus 1 item. And you just do the summation of them and plus this item. If they are bigger than R low, means R low is a valid lower bound. You can just increase this R low until you find what will be like the valid, the kind of the the best lower bound for this one. And the corresponding assortment with just the item I plus the corresponding S prime will give you like the solution of the assortment. Okay, so I just give the details of the algorithm and I just summarize we can prove the regret upper bound, which is epsilon tk squared plus square root of ntk, and this will be a lower bound, and they are kind of a matching if you're just treating the k as a constant. And remember, the k is a cardinality constraint of the assortment. But finally, I just show you like very simple simulated experiment. So actually, we consider two algorithms. One is like our active elimination algorithm, but it's non-adaptive, and the other is adaptive algorithm. And you can consider like a UCB-based multinomial. There are two algorithms proposed by the Columbia group, and they don't consider any outlier behavior. So one is like the UCB algorithm, and the other is Thompson sampling. But they adapt the algorithm to the multinomial logic model, and we report the average regret over t time periods. Okay, so as you can see, there's 100 products. The cardinality constraint is 10, and there are 5% of the customers are outlier. And so you can see, like for the TS and the UCB, so you can see their regret over t, the average regret one just not decreasing, because once your outlier comes in and corrupt your learning estimate, it will take a very long time to recover that. But our algorithm still managed to like kind of decreasing in terms of average regret. And there's another thing that we increase the corruption proportion to be 10%, and you can see like if you don't properly model the outlier behavior, and your algorithm will just almost become flat. But our algorithm, although it becomes very in kind of fluctuation at the beginning, but when your t time series becomes larger, so it's kind of still decreasing. Okay, so I think the time is almost up. So I just make a summary of today's talk. Hopefully it's I don't want to give a very heavy talk. Hopefully you enjoy it. So we'll talk about online learning decision making, especially important for many business applications. I'll talk about some application on online recommendations that make pricing, assortment optimization. The cross-sourcing. But in all this kind of thing, you need to have some model. But the question is that the model is likely to misspecify, and this happens all the time. So robustness is very critical. So in this talk, we mainly focus on extension of the Huber's epsilon contamination model into the online setting to capture the outlier behavior. And we present a paper on the robust dynamic assortment optimization in the presence of outlier customer. So this is more like a kind of a linking like some problem from operation management to like modern machine learning. So thank you very much for your attention. I really appreciate it.
Thank you, Professor Chen, for the great talk. So as for the questions, the first one is that with outliers arrivals, how do we define the regret? It seems, I guess it's S star is just for the typical arrivals.
Yes, so the regret I'm defining in here is just just to consider like like for the summation of 1 to t is still like standard definition of the regret. I don't change the definition. This can be changed. In the paper we mentioned some some other like ways of defining the regret and showing their relationship. But in the talk we just consider a very simple case. Even it's an outlier customer, we just consider this as star to be like a typical customer. Like the best assortment for a typical customer.
Mm-hmm. Thank you.
Yeah. And another question, I think excellent question, is adaptive. So adaptive, very clear, is that in the construction of this algorithm, especially constructing this upper confidence bound, the challenge is that we need to know this epsilon. Okay, I didn't give the detailed format here. You can check the paper, but the epsilon need to be pre-given. This is very difficult in practice because you never go. It's not easy to estimate, especially in the online setting. You just estimate what will be the maximal number of the like kind of outlier customer. So adaptive algorithm is, like you run this algorithm active elimination in parallel with different epsilon. So I can briefly show you here. I think I might have a, I won't be able to go into details. It's a pretty complicated algorithm, but for those interested, like in practice, In many cases, epsilon is unknown and cannot be easily estimated from historical data, so that we need to be adaptive with respect to epsilon. So the idea is that you are using a multi-layer race algorithm, like run parallel like log T threads, and with epsilon j hat is 2 to the minus j, and you run the threads with probability 2 to the j, and smaller epsilon has a larger probability, because the smaller value of epsilon incurs smaller regret, and enforce the coupling of these threads. If item I is removed in the thread j, it's also remove all the threads with a smaller epsilon. So that's kind of saving some time. So that, and with all this complicated mechanism putting up together, you can showing that this algorithm achieve like a poly k times epsilon t times plus square root of nt regret. So this is what I mean by with respect to adaptive.
Thank you. And another question is, maybe I'm missing something, but is your algorithm computationally efficient?
Yes, it's computation very efficient because this algorithm. So the main computation is to check this inequality. Sorry, you need to solve this optimization, and check this inequality is also like solving this optimization. So the key thing that's how to solve this particular optimization problem with the given estimated VJ hat. And we show there is like a searching algorithm. So it's roughly like, like a log T time periods for solving this one. And this is not, you do not need to search like for entrance K. You just moving this boundary and you do like binary search. So this is the only computation challenge, and this can be done by the binary search. So although it looks a little bit scary at the beginning, it's a combinatorial optimization problem, but actually it's not. It's just like a very simple binary search due to this particular multinomial logic structure.
Thank you. And the next question is, was the N0 the number of no purchases or the occurrence of no purchases event like in works of?
Yeah, it's pretty similar, but we do a little bit twist. So N0I is we recall because we need to estimate utility parameter for I. So which means that N0I is the number of times I was selected. So you randomly select an active item. So that you first confine yourself in the times that I was selected, but I was selected, but there are actually no purchase for any item. Okay, so it's not no purchase for item I, it's no purchase for any item. So N0I denotes the number of times within a certain epoch, such that I was recommended, selected, but just no purchase happened in this whole assortment. As.
Mm-hmm. Thank you. And another question is, here you consider the problem where there are outliers, and outliers might be adversarial. So is it possible to consider, say, there's no outlier, but your model is adversarially changing?
Yes, that's a very, very good question, and it's give me a great chance to make an advertisement. It's a very, very recent paper. Let me just go grab it. So actually, it's a very, it's a very great question, because if, why we need to consider this out. So actually, I just do a little bit of advertisement here. This is called adverse. We just have a paper with Yan Junhan from Stanford and Yiming Wang on the adversarial combinatorial bandits with general nonlinear reward function. This is indeed applied to the assortment optimization as a very special case, and this actually is our motivation. And unfortunately, in the 40 adversarial case, the algorithm is very bad. So actually, we can show for the N arms with a subset of K, I think there's a direct algorithm for the multinomial logic model. So so for the dynamic assortment optimization, in the 40 adversarial case, you have N to the power of K and T. And actually, this is both the upper bound and lower bound. So that which means that you have to. So if in the 40 adversarial case, you have to treat each assortment as an arm. There's no way to get rid of N choose K.
Mm-hmm.
So that's the reason why this showing that this model, the epsilon contamination model, is useful, because if you're going too much, you're going to for the 40 adversarial case. You cannot hope anything better than n to the power of k, and this can be super large in practice because like you already think about Amazon, n is like 10,000 and k is like maybe like 10 or 20, and this number just exploding. So for any of you are interested, and this is a highly non-trivial proof, and for anyone is interested in, like I highly encouraged to take a look at this very recent paper we just submitted like about 2 weeks ago.
Yes, thank you so much. And the next question is, the term robust makes me think of the minimax function. Do you use this function in your optimization, or the robust with respect to the outlier filtering?
Yeah, it's only a outlier filtering. It's not related to minimax. I just using this terminology. So I understand robust can get a lot of confusion, but anyway, I'm using this because I just follow Hoover, so he called it his robust model, so I just call it. It's only respect to like the epsilon contamination model.
Thank you. And maybe we have time for the very last question. So have you considered, say, considering this similar problem where you have some outlier, but under the context of, say, linear contextual bandit?
I haven't considered that. If anyone is interested in that, I'm very happy to chat. Yeah, the same thing. It could be a technically more interesting and more challenging problem. Yeah, I haven't done that yet, but it's certainly doable. Like I believe using a similar technique, it's certainly doable.
Thank you very much, Professor Chen.
Yeah, and thank you very much. All good questions. Really appreciate your attention. And happy Friday. Happy weekend.
Yeah, and thank you very much for attending today. And have a nice weekend.
Thank you. Bye-bye.
Bye.